In the previous lecture, we talked about how we're going to minimize the error of the loss function for logistic regression, and then we come up with an iterative method called gradient descent. So let's see an extension of gradient descent, which is a practical sort of version of gradient descent, and we're going to talk about the reasons why stochastic gradient descent is much more used recently in solving real world application in machine learning and deep learning domain. All right, so this is just a recap. So we started by initializing our x, right, x0, the vector. So from t, or for t from 0 up to the point that we stop and return the value, we're going to compute the gradient of t, right? And then we select the direction by the opposite of this. We are going towards the minimization. So we want to find the local, hopefully the global minima, right? We're going to use that as the direction that we're going to multiply with your epsilon, which is the step size, and then we're going to update that for xt plus 1, right? And we're going to iterate over this process until the stopping criteria was reached. So we talked about the stop condition previously. In general, if we want to classify or just define some stop conditions, first of all, the first one is we are interested in having in-sample error of W as small as possible, right? So whenever we felt comfortable, like this is good enough for us, we can stop it. And this is relative, right, to your problem. And the other one is when we are either falling into some of those pitfalls, like we have multiple stationary points, saddle, and we tried our best, and we were still reaching that gradient equal to 0 or approximate to 0. So that perhaps shows we are already in a local or global minima, right? So that's another stop condition. And the third one is like you're just running it forever and you just get tired, right? I'm just going to stop this because I don't want to run this any longer. So the third one could be the number of iteration is too large, or just you set upper limit, and then you're going to say after, I don't know, 10,000 iteration, I'm just going to stop. So these three could be your stop conditions. We also talked about those three different situations that we are dealing with non-convex functions. So although we have a gradient approximately 0, if we had multiple stationary points, in this case x1 and x3, right? So we were to apply other techniques in order to get rid of those. And we also mentioned that in practice, most local minimas are surprisingly good. For instance, x1 and x3. Okay, so that was the first situation we talked about. The second one was when we are dealing with saddle points. Although we have f prime of x as 0, but this point is x is neither a local nor global minima or maxima, right? So we talked about that we can use the second derivation as a remedy to overcome this issue. And the third one was we are getting stuck in flat regions, so like or plateaus, and the practical remedy for this is just to restart or reinitialize and rerun your gradient descent algorithm. So perhaps you're coming from the other side of the paraboloid, right? Or we can choose a larger step size, but this has its own caveats, right? We talked about those as well. So these are the different things that you can apply in order to come up with a good enough stop condition. We also finalized it with the sort of a comparison between the computational complexity, or the big O of gradient descent, and the least squares method, right? We come up with this O of the order of n D, and N was your number of observation or the rows, and D was the number of your features, right? So we mentioned that gradient descent in general has an asymptotic, right, O and D, and least square because of those converting of pseudo inverse, and the final product. So you would have these three O's, and depending on the size of N, so if N was much larger than D, so this would be the dominant of these three rather than this, right? So we would have had an upper bound of O as an asymptotic one of order of N D squared, right? So we sort of concluded that exact solution in many problems is an overkill. So in practice, we might just have to run few iterations. So this few could be 100 or in the order of thousands, depending on the problem, right? All right, so we reached up to this point. Let's see what, yeah.
Can you tell what N and D are?
So N is the number of rows. So I've forgotten to bring my pen, so I'm just going to write it on the blackboard today. So that was your D here, right? X0 up to XD. And these are your observation, right? So you have N of those. This is N. Okay. So suppose, let's talk about it first visually, and then we're going to formalize it later on. Suppose you have two x's, so like x1 and x2, and that would be your second one, which was the A in. So if you draw this, the optimization space, that would be something like this. And then so on and so forth. So there, it's kind of hard. Okay, and that would be your global minimum, right? So using gradient descent, which we talked about it last session. So we would start. We had a training data of x1, y1 up to xn, yn, right? Would be your D, and this would be your N. So suppose you're talking about a huge data set, like statistics from like census of Canadian demography, like 35 million people, right? So you would have 35 million records of these. So in order to calculate the gradient descent, as we talked about it last session, the order was ND. And we also talked about that this is much better than the ND2 of order of the least square. So we prepared this one over that. But now we're gonna end up, we're gonna run into another issue, and that would be the case that in order to calculate each of the iteration of your gradient descent, for this case, you have to iterate over 35 million data points to make the first guess. So suppose you start from this point on GD. So in order to calculate this point, you have to do it for 35 million iteration, right? For all your data set. And then after that, you're going to calculate the gradients, and then on the next step, you have to do another time this 35 million iteration. And that's why you have order of ND here, to just find maybe your second point and go towards here, right? And this process should go on and on and on, but eventually we know that it's kind of converge to your global minima, right? So in this case, say 1, 2, 3, 4, 5, 6, right? So if we modify the algorithm to avoid this calculation of summation of all these 35 million data points and just focus on one data point x1, y1, or xn, yn at a time, and we pick this one among all those 35 millions randomly, that's why we call it a stochastic gradient descent, we're going to have a much, much lower order, right? We're going to downsample actually this one to just, this order of D on the case of stochastic gradient descent. So in this case, we shuffle the data because we want to make it as random as possible, because a stochastic means that you are trying to deal with random variables, right? So you have to shuffle and reorder your data. So out of this 35 million, we want to pick our x1, y1, and given that point, we might start from here. I'm going to put it with circles here, SGD. Like, we might have a start here if we shuffle more, you know, who knows. Could be another one, either of these. So say we pick this one, and we calculate the in-sample error and the loss function, and then we're gonna start from this point. Then on the next, so now given this point, we're gonna tweak a little bit our loss function using the gradients so that it fits better for that specific point only. Then we might go towards this direction, and then again here we take into account our second data point from our 35 million, and only for that we calculate the gradient that fits the loss function better towards minimizing loss function, and that would be this. At some point, because we are randomizing our selection, we might even go in a worse direction. Like instead of going toward this, we might just come back here. And then, but if you carry on this process for several iterations, you see that eventually it helps you to find the final path towards your global minima. That's why you see in your graphs, when you train a neural network or other models, you see when you plot them, you see all these wobblings left and right, because that was the case for each of those data points that you choose. And then finally, you might end up somewhere here. The difference here is the stochastic gradient descent, since we don't take into account all the data points at once, we never converge to the optimal point, which was our global minima. But we're gonna traverse somewhere around here, and then it's gonna go back and forth, go back and forth. So we're gonna end up somewhere around a good enough point that is acceptable for us. So that's the major difference between a stochastic gradient descent and the full version of gradient descent. But since this has a much lower order, we can apply it to many more, bigger data sets. That's why it's been used much more often than the gradient descent itself. So that's a default version of a stochastic gradient descent. So say instead of taking randomizing the data and shuffle it and reordering and then choosing one by one, we would choose, instead of one, we would choose a batch of m, and m could be like any number, I would say, and that would be your size of D, right? Data set, data. So say instead of choosing one, we choose like 20, we choose 100. And we call this batch. So instead of choosing one by one, we might choose a batch of like 10, a batch of 20, and we fix and we using the gradient that we get, we optimize our loss function and we minimize it using those batch only. So this version would be called batch stochastic gradient descent, and that's another variant of the full version gradient descent. I mean, we're going to have so many other variants that you might see in the literature and other optimization apply. How are we going to deal with those selections? Are we going to save them? Are we going to cache them somewhere? And then that's why you have other type of gradient descent as well. Yeah.
Could you also have like batch gradient descent?
How are you going to select those batches? If you randomize them, it's going to be a stochastic again. If you deterministically select them, you might end up on a new path. But since you didn't reorder and shuffle your data, you're going to be bound to the way you chose, right? So it's not going to be helpful. Maybe at some point you might not converge. All right. So that was the whole thing that I wanted to describe today. First, I thought we're going to talk about it visually, and then we're going to formalize it. So like in TensorFlow, sometimes when you train your model and you use a stochastic gradient descent, instead of, that was your iterations, that would be your E error. So you see with the gradient descent, you sometimes go like this, going down. That would be your gradient descent. If you use a stochastic gradient descent, sometimes you go up like this. That would be a stochastic. So this behavior is because of going left and right, because of the choosing different choices you had at those specific iterations.
In the graph you just drew, yeah, wouldn't the gradient descent approach zero like much slower?
Gradient descent approach zero actually faster because you're iterating over all your data points and eventually you're going to converge. With the gradient descent, you're sure that you're going to converge to the global. If the function was convex, yeah, you're sure that you're going to converge your global minima. But with a stochastic, you're sure that you're going to be within a boundary of that, and which is good enough. Like you're surprised. So like you see, for instance, training AlexNet on ImageNet, if you train it for like, given the default hyperparameters, if you train it for 2 million iterations, so you might have a loss of like 1.25, and your prediction was, your top 5 prediction was like 77%, right? You go up to 5 million, so like 3 million more iterations of training, your loss would come down maybe 122, and that would increase your top 5 like 1% only. If you go over to 10 million, your loss would just go like 21.9, and that would be like 7.9%. So you see, 8 million iteration later, you just found a little bit better, within the boundary of your global minima, and you increase your top 5 accuracy. We call these top 5 to like which is 1%, which is like somewhere around here. You might just go 20 more million and you find like 0.5% better. But you see, before that, you converge already to a good enough point that your prediction level was already good. Let's formalize this. At each iteration k, we're going to select one sample, and that sample is coming from a uniform distribution, right? That's why we call this unif. And then, if you want to update the w's, it would become wk plus 1 equal to wk minus epsilon multiplied by the gradient of en. As before, we had this. So the capital E, the overall is is 1 over n of all those pointwise, right, losses. And I'm sure you all know what the uniform distribution is, right? Yeah. So, for all of those points, the probability of having a loss for n from 1 up to n equal to capital N. So, because it's a uniform distribution, you need to sum them up, right? So the probability of n equal to 1, the gradient of E1, WK up to PR n equal to capital N, the last one, the gradient of En of WK, is going to be 1 over n, summation of all those ENs. Okay, and then I was talking about this. If we use a stochastic gradient descent, it's going to be a noisy estimate of the true gradient descent, but still it's practical. It's a lightweight, so we can use it in many different domains with energy with computationally limited devices, right? They say computationally constrained devices, such as your cell phones, embedded domain, and other things. So, a full or a true gradient descent gives you an exact gradient, right? The order is a big O of nd per step. However, a stochastic one, SGD, gives you a noisy estimate of the gradients. Thus, the big O is going to be only d per step, right? So why don't we use this in more iteration rather than the first one? And that's exactly why we are doing it. Questions? Yeah. Then another extension of SGD was to use a batch instead of a single data entry, right? So at random, we can use this summation will go over from 1 up to m now, okay? Because we are selecting m examples, so we have to sum them up at each of those n iterations. And that's how we update the weights, okay? Of course, the advantage of batch, which is used in many different machine learning tools as well, is you can better parallelize it, and you have a better estimation of in-sample error. So, for instance, in neural network that we'll talk about starting from perhaps in 2 or 3 sessions, they do an update once per each batch, right? They store all the local updates or the partial updates, but they're not going to affect it. They're not going to save. They're not going to spend their computation per input. They're going to wait up until the first batch of 50 or 100 arrived. They gather all the updates, and then they update once, okay? And this way you are just saving your computations and also time in order to train. At the same time, you can parallelize this. You need to have some sort of synchronization and in place, but in general, batch mode SGD is used currently in like TensorFlow. If you're using it with your CPU, it batches over many threads, or if you're using with your GPU, it's gonna even use more threads, but because GPU threads are more flexible and much higher in number. That's why it's gonna converge faster at the end of the day, with least computations needed. So these are the advantage of having a mini-match SGD. So let's have an example to how we're going to drive SGD update, right, using our previous formula. So as we know, in sample error of W was the summation over all your pointwise, right? And in the case of logistic regression, we have, right, each of the pointwise losses of your vector W is equal to the log loss, right? Log 1 plus e to the raise of minus yn W transpose x, okay? And we mentioned that this is a convex function in W, right? So let's see how we're gonna find the exact SGD update for logistic regression. So we just have to expand this. So we put in place this. So for computing the gradient with respect to W's, so En of W is equal to the gradient of, with respect to W, the log of 1 plus e to the raise of the rest of the things you had minus yn W transpose xn, right? So now what we're going to do is, first of all, we can get rid of the log and bring it outside. So when you bring that outside, it's going to be 1 over whatever it was in front as a denominator, right? So you have this divided by 1 plus e minus e to the raise of minus yn double transpose xn. So these are coming as a denominator. We got rid of log. What we have to deal right now is the rest of the thing here, except the log. Again, this is e to the raise of something, so the derivation of that, the derivative of that for the gradient is going to be that amount. And then you have, so by now you got rid of the e as well here, right? So whatever left is only minus yn W transpose x. Is it clear up to now? So we arrived to this point. Now we need to continue with now we can factor that minus yn xn out of the equation, because that was what coming out of this, right? We are computing the gradient with respect to W, so W is our variable. So whatever left is the coefficient of that. So you have minus Wn xn, right, with the rest of the things we already brought out from the gradient. And then if you combine this and add it to the formula, you're going to find that this is the final result. Okay, thus we can say, in order to update the update rule using a stochastic gradient descent for logistic regression would be wk, your current weight, plus epsilon of k multiplied this amount, y of n xn divided by 1 plus e to the raise of yn W transpose k xn. Okay? All right, so now let's have a comparison between SGD and your Perceptron algorithm. let's see if we can find any resemblance between these two. Are these two sort of an extension of each other? Is one an extreme case of the other, or whatnot? So let's see what are the relation between these two. So that's the update for SGD. I put it on the top right side, right? So if we expand Perceptron algorithm, interestingly, we can see that there is a close connection to SGD. So let's talk about two cases in a class of binary classification, right? When we're dealing with Perceptron, so one case would be this is a misclassified point, and the case two would be that was a true classification, so that was a correctly classified point. Let's see on the first case how we're gonna come up with a closer formula using Perceptron. So if this is a misclassified point, right, the value of this, the output of this would be negative. Does that make sense? Why? Okay. If the value of this is negative, right, when you make that value an exponent of e, right, because it's e to the raise of something negative, so it's going to be pretty close to 0, right? Thus, if you want to have an update rule using this for the case of Perceptron, the update rule would be wk plus 1 is approximately wk plus yn xn. Because this amount was approximately 0, right? Whatever left was this on top. So the denominator became 1. Okay? Is it clear? So that's for the first case that your classification, your prediction was wrong, right? It was a misclassified point. Now let's see on the case 2, you had a point correctly classified. Let's see what's going to be the relation between these two. So now in this case, this will be positive, right? If this is positive, again, just like what we had with the, so this is the e to the raise of x. So something like this, right? This is 1 where it takes 0, and then at this 1 it is e, and then you're going to go towards nonlinear growth. So if the value is positive now, definitely the output of e to the raise of that value is going to be way, way more positive, because it's not even linear, right? The growth is exponential. Thus, we can say the output of that, which was here, is going to be pretty close to 1, because this is a large number, so it's going to bring down everything. And what's left is only an update, which is no update. Because why would you update if you have a point correctly classified, right? So you see that by comparing these two classes of solvers, now you see that actually Perceptron update is sort of an extreme case for logistic regression plus SGD, right? It's like it's a very small subset of applying SGD over a logistic regression. Okay, it's a special case of that.
So this makes sense because there are only 2 classes, right? That's why we don't need the 1.
Yeah, that's right.
Classes, we have to even wait for it.
Yeah, if you add more classes, it's going to expand our misclassified permutation even more, right? Instead of 2, we have to permute more, because at some point we have misclassified the first one perhaps, or the second one, or the third one, so you have to expand that, yeah. All good? All right. So just like I mentioned before in the previous lecture, we can also apply a stochastic gradient descent for least squares method because those required, again, those methods were computationally intensive. So we can also use the SGD, which was an extension of GD for both linear regression, and we already were using it for logistic regression. So if you use it for that, you can also apply for linear regression, in which you had to find your En of W from the square error method, right? So in this case, you have a batch size of, I don't know, you can call it Bm, and then apply it. So that's the resemblance for that. So let's just put everything together, what we've seen in this lecture for a stochastic gradient descent. So for every epoch that I mentioned there, it's just one level higher than your batches. We randomly permute training set, right? We shuffle the training set and test set, so we are using the training set that we shuffled at each epoch. And then we are trying to come up with a specific, portion of that training set as our batches. So that'll be from J1 up to JB, right? These are the number of batches. So we have B batches. And then we're going to define S of J as an index set of next batch of B. And then we use the same update rule for gradient descent, including the number of batches, right, for each of those. So we are in batch now for update. So the W will be W minus epsilon divided by N, and a summation of all of those gradient En of W. And then finally, we can end this loop and end the first one for the epoch. And then again, we're going to check for the stop condition, just like we were checking the stop condition for gradient descent itself. Those, make sure if it's convex, we have the gradient approximate to 0. If they're non-convex, you have to just deal with the specific situation. Are you going to restart it? Are you going to use the second derivative? Are you going to have a larger step size? How are you going to regulate that? And for some of these, we're going to learn some of the techniques we're going to learn next lecture. A technique called momentum that regulate the step size, and another regulator which is called Adam. And then gradually we start looking at multi-layer perceptron, and then going towards neural network from perhaps next week on Wednesday. All right? Is there any questions for today? Okay. If you guys had any questions about your assignment, either email me or your TA, which you can find his detail on the course announcement. Check the course announcement, you can find his email. And yeah, good luck on doing your assignment. Have a good day.